A little bit about me. So my name is Alon Wolf. I started learning C++ in high school because I wanted to make video games. Before that, all I knew about C++ was that there was a pop-up I needed to click on whenever I installed a new game. Today, I am working as a senior software engineer at Medtronic. Where I work, we make robots for spine surgeries, so I get to do what I love while also helping to improve patients' lives. In my spare time, I write a technical blog and participate in game jams, and I also enjoy experimenting and trying new things in C++. Okay, so in this talk, we are going to take a deep dive into the world of compile-time parsers, but we will also cover other aspects of the C++ language. So I hope you will find it useful, even if compile-time parsing isn't your cup of tea. About the structure of this talk. First, we are going to cover expressiveness in C++ and how we can write more expressive code. Then we are going to take a look at open source compile-time libraries. For each library, we will look at its API, design, and some implementation details. Finally, we will see how we can use compile-time parsers to implement reflection features and show how we can use them to implement some examples, such as creating functions, types, and tree data structures. Okay, so what is a parser? For our purpose, a parser is something that takes an input, like a text or tokens, and returns a value or a parsing error. For example, in a compiler, the text is converted by a tokenizer into a tokens, which are then passed to the parser to create the syntax tree. Or in a web browser, we can use a JSON parser to convert text into a JavaScript object. So there are many ways to create parsers. One common way is by using parser combinators. A parser combinator can create a new parser by combining existing one. So, for example, if we have a function that we call parseString that takes the input string and the current parsing position and returns a string or an error, and we have another similar function called parseInt that takes the same arguments and returns an integer or an error, we can combine them to create a new parsing function that returns a string or an int by first calling the parseString with the parameters, and if it fails, calling the parseInt function. Because all the functions have the exact same input arguments, we can simplify this pseudo-syntax and remove the function arguments. Another way to create parsers is with parser generators. So a parser generator can create a parser from a grammar definition. Some popular parsing algorithms that are used in parser generators are LL1, LR1, LALR, and many others. Here you can see an example of a grammar definition that uses the EBNF syntax. So in the final line of this example, we can see that an assignment is defined as an identifier, followed by colon equals, followed by a number or identifier or a string. Okay, now let's talk about expressiveness in C++. What do we mean when we say expressive code? We mean a code that communicates its purpose. For example, what it does, how it should be used, or why it was written. And it relies on two things: the syntax of the programming language and the naming convention. In this talk, we will focus on the syntax part. As the language evolves, we get new syntax that we can use to write more expressive code. Here we have two examples that create a vector with 4 integers. The C++11 example is more expressive because it has less boilerplate. It doesn't need to create a C-style array or use sizeof, both of which burdens the people who need to work with this code. Another way we can make our code more expressive is with operator overloading. We can use operator overloading to write operators that call a costume function for specific types. So in this example, by using the division operator, our code can be written from left to right and without parentheses. Also, the division operator is a good choice for path concatenation because it is a common way to represent paths in many operating systems. So, domain-specific language, or DSL, is a language that is designed to solve problems in a specific domain. So, after we learn the syntax of the DSL, we can use it to more easily solve problems in that specific domain. Some examples of DSLs include SQL, CSS, regular expressions, and makes that we use to write make files. Here we can see an example of an SQL parser that uses the Boost Spirit library. Boost Spirit is a library for writing runtime parsers, and it has a DSL. In this example, we first define text as all characters that aren't opening angle brackets. Then we define node as either XML or text. Then we define start tag, end tag, and finally, we define our XML parser as a struct tag followed by a list of node followed by a matching end tag. This is all valid C++, and as you can see, we can make it look like a completely different language. But there are still limitations. The syntax must be valid C++ because it needs to be parsed and compiled by the C++ compiler. So if we take a look at a small part of code from the previous slide, the syntax for list of node is starred followed by node. Let's assume we want a different syntax for our DSL. What if we wanted to write node star instead? Well, in this case, we will get a compilation error because in C++, the unary star operator must be on the left side of the expression. Okay, now let's do a quick recap of everything so far with a filter transform example. So here we have an input vector of cats, and we want to get all the cats over the age of 42. And we want to get just the ID and name of them. So we use iterators to iterate over the vector. We check if the age is bigger than 42, and if so, we place a tuple with the ID and name. We can use modern C++ syntax to replace the iterators with a range-based for loop to make our code more expressive. But this is 2023, and we have ranges now. We can use the overloaded pipe operator to chain multiple operations, and now our code literally says filter transform. But what if we wanted to write it in SQL syntax? So we can do it by using a parser. First, we create a parser. Then we use the parser to parse the SQL syntax into a function. Finally, we call the function, and we are done, right? Well, not exactly, because there are some differences. First, we have the runtime overhead of creating the parser and parsing the string into a function. Then we also have the runtime overhead that our result type must be type erased, for example, by using a vector of stud_any. This is because it depends on the parsing function is the output of the parser, which is only known at runtime. So at compile time, we don't know what type we get. We can solve all three problems by shifting the parsing to compile time. Now we don't have the runtime overhead of creating the parser, parsing the string into a function, and we also know at compile time the output of our functions that we parsed. So we know the type of the result. Finally, we can wrap the parsing logic with a string literal operator. This is the syntax for it, for those who haven't seen it. And now our filter transform code is a single line of SQL-like syntax. Okay, so let's generalize what we've just seen. In this example, we used compile time parser to convert SQL syntax into a function, or more specifically, a lambda. But the general case for compile time parsers is that we can use them to convert any costume syntax into any compile time value. Is something like this even possible? Well, spoiler alert, the answer is yes, and by the end of this talk, you will know how. But we need to start from the beginning, which in my case was a Google search. So I asked, hey, did anyone try to do this crazy thing in C++? And the result was, of course, there is already a Boost library for it, which leads us to the first library of this talk. Boost Metaparse is a compile-time parsing library by Abel Sinkovich. Everything in this library uses C++ 98, except for the creation of the compile-time input string. So in C++ 98, we have to write each character as a separate template parameter, while in C++ 11, we can use the Boost Metaparse string macro with a string literal. For compile time computations, the library uses template structs, which are also known as meta functions. A typical parser in Boost MetaParse is a struct that has an inner apply meta function, which takes the input string and the current parsing position and returns the parsing result with some additional information. So let's talk about the syntax of meta functions. The syntax and techniques needed are pretty horrendous, and this is not me saying, it's from the official C++ core guidelines about template metaprogramming. While you may say that pretty horrendous is a bit harsh, having to express everything in terms of template structs instead of if branches, for loops, and other basic syntax element is definitely not something that we would like to do. In the slide, you can see part of a calculator parser implementation that uses the Boost MetaParse library with template metaprogramming and judge the syntax for yourself. Okay, let's go over some features of Boost MetaParse. You can use it to parse a string into a compile time meta function or a runtime regular function. The difference between them is whether the parsing result is a meta function, or also we can call it template struct, for compile time function, or for runtime function, it's a struct that overloads the call operator. Another feature of Boost MetaParse is that you can use it to write meta function in Haskell-like syntax, which you might prefer over the metaprogramming syntax. In this slide, the meta underscore edge ace is a compile time map. The import call adds a new meta function to the map. The define call creates a new meta function from a Haskell-like syntax and adds it to the map. Each call returns the new modified map, so we can nicely change them together. In the end, we can get the new meta functions from the map to use them in our regular C++ code. We can also use Boost MetaParse to create a parser for grammar rules. For each rule, we need to define the syntax rule that it contains and an optional semantic action to take. Okay, now for some implementation detail, let's see how the Boost MetaParse string macro works. What I want you to take from this is not the inner working of the macro and how it is in the complete implementation, but more to see how difficult it was to create a compile time string using C++11. So the macro expands to something like this: a call to make string with the length of the string, followed by many calls to str@, with the input string and the running index. str@, is a constexpr function that takes a string and an index and returns the character at that index, or 0 if the index is past the length of the string. So after evaluation, our call to make string looks something like this: the length of the string, followed by the characters of the string, and then a lot of trailing zeros. In C++11, constexpr functions were limited to a single return statement, so this is pretty much the limit of what was possible. The makeString function recursively concatenates the string until it reaches the original length. So it removes the trailing zeros, and we are left with the original string as a compile time string. Look how much effort and tricks were necessary to create a compile time string in C++11, something that we can now do with just a few lines of code. And with that, I think we can move to C++17. So Lexi is a compile time parsing library by Jonathan Mueller that uses C++17. It has a DSL for writing parser combinators, and it supports Unicode string and compiling and parsing at runtime or compile time. We can create a parser by defining a struct that has a rule and a value. The rule defines how to match the input string, and it can be implemented as parser combinators. The value specifies how to store the parsing result. constexpr has become a lot more powerful in C++17. So now we can use an immediately invoked constexpr lambda to define our rule constexpr value. And inside the constexpr lambda, we can write code with the same syntax that we use to write regular C++ runtime code. Lexi has an online playground that includes many examples. On the left window, you write the parser. On the right window, you write the input string. And the window below shows how the parser matches the input string and constructs the result. Everything is interactive, much like a compiler explorer that we all know and love, and it is a great tool for learning how to use Lexi and prototyping with parsers. As I mentioned before, Lexi can parse at runtime or compile time. In terms of runtime performance, here you can see a JSON parsing benchmark, and as you can see, Lexi is on par with other popular JSON libraries. So we get a library that can parse at runtime and compile time without sacrificing performance. Okay, this is how a typical parser in Lexi looks like. We have an outer struct with an inner consexper parse function, similar to the outer struct with the inner apply meta function in boost meta parse. But this time we have between them another template struct called indirect that takes a next parser template parameter. The parse function can invoke the next parser with additional or modified arguments. This design decision solves the problem of dealing with different return type, such as optional, tuple, or variant. The results are simply parsed to the next parser when we call it. So let's see how a sequence parser combinator is implemented in Lexi. So what is a sequence parser combinator? It takes two parsers, P1 and P2, and creates a new parser where P1 must be followed by P2. In Lexi, a sequence parser is easily implemented by defining an alias that rewires the next parser template parameter. So during parsing, P1 will invoke P2, which will then invoke the next parser. Okay, we've seen two compile time parsing libraries. Now it's time for something different. CTRE, or compile time regular expression, is a library for compile time regular expressions, and it was created by Hana Dusikova. The library can perform regex operations like matching, searching, and capturing at runtime or compile time. And it also supports Unicode strings. We can create a regular expression by using the CTRE literal operator or by passing the regex pattern as a string literal, as a non-type template parameter. One limitation of the library is that the regex pattern must be known at compile time. But it is already a common practice to have the regex as part of the code, for example, if you want to parse a date format. Okay, now let's talk about performance. So the construction of the regex from the regex pattern string happens at compile time. So there is zero runtime overhead, and performing matching and other operations can be done at runtime and compile time. As you can see from this benchmark, CTRE is much faster than stud regex and have similar performance to boost regex. So let's see how the CTRE literal operator works. We have a struct that we will use to represent our compile time string that we will call fixed string. And it has a consexper constructor that takes a fixed size array and copy it and store it in itself. When we call the CTRE literal operator, it will construct a fixed string from the string literal. And then inside the CTRE literal operator, it will pass the fixed string into the regex object and return it. Look how much easier it is to create a compile time string compared to the boost meta parse string macro. Okay, in order to parse the string to a regex, CTRE uses LL1 parser. The LL1 parsing algorithm takes the input string. Eternally, it has a stack that it pushes and pops values from, and it also has a parsing table that represents the grammar rules and is used to determine which action the algorithm should take next. The stack of the LL1 parser is implemented as empty struct, and performing operation on the stack, such as pushing and popping values, is done with overloaded functions. The LL1 parsing table of the regex grammar is also implemented as empty struct and overloaded functions. I think this is a very elegant design decision that shows how such a complex system can be implemented from these two basic building blocks. So the parsing loop takes the input string, the current parsing position, and the stack. First, it will call the overloaded rule function of the grammar, which essentially performs lookup into the parsing table. And then it will decide what to do next based on the action. So we can return an error or success or recurse to the next iteration with modified parameters. Okay, after we have seen how LL1 parsing works, we can move to a different library, but this one uses the LR1 algorithm. So compile time parser generator, or CTPG, was created by Piotr Winter and uses C++17. As the name suggests, we can use this library to generate parsers from LR1 grammar. You can use this library with your own costume lexer or let it generate one for you. Okay, in order to generate a grammar, we first need to define the terminals and non-terminals that will be used in the grammar. We can define operator precedence, for example, so that multiplication will be evaluated before subtraction, and we can also define associativity, so that if we have a chain of subtractions, they will be evaluated from left to right. The library also allows us to define a terminal with a regex pattern. As you can see here, this will match a number. Okay, we can combine our terminals and non-terminals to define the grammar rules and generate the parser. The rules are created with an expressive DSLs, and we can create recursive rules because all the non-terminals have already been defined. Okay, now I can't possibly cover the entirety of LR1 parser in a single slide, and it is a big topic that deserves a talk of its own, but I would like to highlight one implementation detail that is used in CTPG. So here is a quick overview of how LR1 parsing works. First, the LR1 parser generator takes the grammar rules to create item sets that represents every state that can be reached during parsing. It then computes the parsing tables, which will be used to transition between states during parsing. Here you can see an image that represents the item sets and the transitions for a grammar. And in many runtime implementations, they are often implemented by using a set or a map. But how can we do it at compile time? Because we don't have context per set or a context per map in C++. So how does CTPG do it? Well, an LR1 item is defined as a struct that has three data members. One that contains the index of the rule, the next contains the current position inside the rule, and the last contains the next terminal that can follow it. This is the one in the LR1 for the look ahead. CTPG computes the maximum value for each member in the LR1 item. So here we have the number of rule, the maximum number of positions, and the number of terminals in the grammar. Then it multiplies them all together to compute the address space of all possible LR1 items. And so an item set is implemented as just a bit set of the address space for all the items. Finally, it defines functions to convert back and forth between an LR1 item and an index, so that adding, removing, and finding items in the item sets are just basic bit-set operations. It shows that some problems of compile-time code can become a lot simpler if we can find an upper limit and use a fixed-size container. Now, let's move to C++23. Okay, so macro rules is a library created by Maxim Pasichnik, and it uses C++23. We can use it to create a DSL with Rust's macro rule style syntax. It is more of an experimental proof of concept than a full library. Before we take a look at the library, here is a quick overview of Rust's macros. Rust have two types of macros, procedural macros and declarative macros. Procedural macros, or a proc macro, is just a function that takes a token stream and returns the token stream of the new generated code. We can call a proc macro directly, or pass it to another macro, for example to the derive macro, which will invoke each one of the macros in parentheses with the tokens of the struct below it. This library isn't about proc macros, but at this point you can already have an idea about how they can be implemented in C++. Declarative macros use the macro rule syntax, which contains two parts. The first part specifies how to match an input pattern, And the second specifies how to transform it into an AST. In this example, the macro rule vec will match a list of expressions separated by commas, and it will generate a temporary vector, generate a push call for each of the expressions, and return the temporary vector. Let's see how we can do something similar in C++ by using the macro rules library. First, we declare a struct called sum that inherits from a macro rules pattern. And so to specify which syntax we match. So in this example, we will match the word sum followed by a list of arguments. Then we need to define a transform function that will take the context of our matching result and return the output. From the context, we can get a list of arguments, pass them to std_apply, and use fold expression to calculate the sum and return it. We can invoke the new sum macro rule by calling apply rules with the name of the struct and the text that we want to match. Internally, the library uses a compile time parser to create a template that represents the AST. You can also write the template directly instead of using the macro rules macro. But I think the syntax above is more expressive and easier to work with. Okay, so identifier in macro rules are only used for lookup and equality comparison. So they are converted into 32-bit hash values because it's easier and more efficient to pass them around than a variable size string. If we look at the implementation of apply rules, we can see that it is a preprocessor macro which converts the text to string literal and passes it to a function that does the matching and transformation. Here are some things to keep in mind. We're using a preprocessor macro to convert text into a string literal. The first thing is that comments won't be included as part of the string literal, so you get support for comments for free. In every editor that I tested, syntax highlighting kept working inside the macro. And the last thing to keep in mind is that if you have multiple white spaces, they will be reduced into a single white space. So keep that in mind if you are thinking about having a syntax that relies on one space, on white space for your DSL, like in Python, for example. Okay, here we have the final compile time parsing library for this talk. This is a very lightweight one that I wrote for myself. And we will use it to implement some examples. It has a DSL similar to Lexi and Boost Spirit for writing parser combinators, and it returns fixed size containers. So if we have the binary OR operator return a variate parser or an OR parser, so it will parse an int or a double, and it will return a variant of it. The bit shift right operator is a sequence parser, so here we have int that must be followed by a comma and then by a double, and it will return a tuple. The star operator is a list parser, as we've seen before, and it will return a fixed capacity vector. And finally, we can use the bit shift equal operator to pass the output into a lambda. Okay, we can use C++23 std_expected to represent the parse result, which can be a value or a parsing error. A parser in this library is just a wrapper around a stateless lambda that takes a parsing context by reference and returns the parsing result. The parsing context is a struct that contains the input string and the current parsing position. We can define concepts that check if a type is an instantiation of the parser template. It is implemented by calling the parser constructor with a concept argument and checking if they have the same type. We want to have different implementation for the sequence parser combinator, depending if we want to combine two parsers or we want to append the parser into an existing sequence. This is done by using concepts. The concept for sequence parser checks if the type is a parser and also if the inner function of the parser is the sequence parsing function. Therefore, it is more specific than the regular parser concept because it includes the parsing concept and also another concept. Because it is more specialized, the call to bit shift right operator will reach the correct overload function, and we will not have an ambiguity error. One limitation of compile time parsing is that the input string must be known at compile time. So now I have a question for you. Which string is used in every C++ application and was always been known at compile time? Yes. Yes, exactly. It is the source code because it is the input to the compiler, so it must be known. Which leads us to reflection. And we will see some interesting ways that compile time parsers can be integrated with reflection. But first, here is a quick overview of the state of reflection in C++. So C++ has many introspection features, but having reflection as part of the language is still far away. Here are some libraries that you can use right now if you want to get reflection working in C++. A common approach of reflection libraries is to use a macro to generate the reflection metadata. For example, in the rare CPP library, you can use the reflect macro inside the class to reflect all the data members, or outside of it to reflect just the public ones. We can use compile time parser to generate the reflection metadata. Here we have macros that uses the same text twice. Once it passes it as is as source code, and another it converts it into a string literal and passes it into a compile time parser. While it is not a viable approach to try and parse the entire C++ syntax at compile time, it is possible to write parsers that parse just part of the syntax. For example, the attributes of a struct. In the code here, the macro generates a context per function that returns the attributes of the struct. We can define two separate macros that will call compile time parsers. One will parse the attributes, and another will parse all the data members. Then we can create a new macro, which we will call derive, that we will invoke each one of the macros in parentheses with the string literal of the source code and pass it to them. And this is one way to implement Thrust derive macro and create a similar system to procedural macros in C++. But a more interesting use case is when we leverage reflection to empower compile time parsers. For the sake of fitting the code in slides, the word identifiers were shortened to ident. Here we have a static member function called resolve identifier that maps an identifier to a pointer to data member. It uses function overloads as lookup table, and it computes 32-bit hash values of the string literal, similar to what we've seen in the macro rules library. We can wrap it in a repeating macro to generate a resolve identifier function for each one of the data members. Then we can create a function to get a data member by an identifier. It will first call the static resolve identifier function of the struct with the current identifier to get a pointer to the data member, and then use the pointer to data member to get the actual data member from the object. And so we can use it to get a data member of an object by an identifier string. Okay, now let's see how we can integrate reflection with compile time parsers to implement a syntax that returns a nested data member. It will be a starting point that we will build upon later. The syntax is a list of identifiers separated by dot. And okay, now we need a function, and this is how a parser looks like. It just parses a list of identifiers that is separated by dots, and the output is a fixed size vector with 32-bit hash values for each of the identifiers. Now we need a function to get the nested data member from an object. This is an approach that I sometimes use when writing compile time code. I first write it as a pseudocode-like runtime code, just to get the basic logic going. So first we create a result vector that points to the input object. Then we iterate over data member and call get member to get the next nested data member and store it in the result. Finally, we return the result, which will be the most nested data member that we want to get. In order to make this code work, we need to make some changes. First, we take our compile time argument and move it into a non-type template parameter. So in this case, we move the members from being an argument into a non-type template parameter. The next step is to replace loops with recursion or a fold expression. In this case, we replace the loop over the members with a recursive lambda, which we can easily write in C++23 by using the recursive this. So if you can see in the beginning of the lambda, we have this auto-ref self, which refers to this lambda. So when we call self, it's a recursive call. Finally, the last step to make it work is to replace branches with if const expr. In this case, we only have one branch that checks if we need to exit the recursive lambda. So we just, instead of if, write if const expr. And now we have our function works. Finally, we can wrap the code to parse the input string into the list of members, and then call our getNested functions that we just implemented inside a string literal operator, so that we can have this nice and expressive syntax. Okay, now let's look at the generated assembly. Do you see it, or wait? Okay, so here we have two functions, f1 and f2. One of them uses the regular C++ syntax, and another uses our new syntax that we used with compile time parsers. As you can see, it has generated a lot of code. What you will not find in this code is any of the parsing logic or the input string. All of this is just the implementation of the getNested function. The reason there is so much, the compiler generated so much code here is because I compile it with O0 optimization. So it essentially emits the code as is without any optimization. Let's increase it to O1. And it removed all of the boilerplate. We are left with the exact same implementation for the regular C++ syntax and the compile time parsing syntax. So it is a zero runtime overhead abstraction. Okay, let's extend the syntax and add two new operators. The colon operator will perform a range-based for loop, and the pipe operator will call the function with the current value. First, we need to create parsers that supports the extended syntax. So the pipe parser will match a pipe followed by an identifier, and it will return a pipe struct that will hold the 32-bit identifier of the function that we need to call. And the iterate parser will just match a colon and will return an empty struct. Finally, our new extended parser will be a list parser that each variant can be either a pipe, an iterate, or a list of members to get the nested member function. So now we need to implement the implementation function for our new extended syntax. So we use a recursive lambda, similar to what we did in the previous example. And for each iteration, we check the value in the current variant. If we have a list of members, then we call the getNested function with the current value and pass it to the next recursion. If we need to perform a range-based for loop, then we perform a range-based for loop and pass each element to the next call of the recursive lambda. And finally, if we need to call a function, then we can get the identifier from the pipe struct. And what do we do now? We need some way to call a function based on an identifier. Well, it can be done by using the same technique we used to get a data member, but this time we use a free function called resolve identifier that will map an identifier to a function. In this case, we map the square literal to the square function. And we can wrap it in a macro to reduce boilerplate. So now we call resolve identifier to get the functions that we need to call, and we get the function and we call it, and we are done, right? Well, actually no, because the lookup for resolve identifier will be based on the scope of the implementation function and not where the syntax is used. For example, if the resolve identifier is defined inside of a namespace, it will not be found when we will try to call the resolve identifier in the implementation function. We can move the call to resolve identifier from the implementation function into where we use the syntax and pass it to the implementation function as a lambda. And now it will find the square function. We can refactor the lambda that calls resolve identifier into a macro, which we will call scope. Because our scope is just a lambda, we can also create one that maps an identifier to a local variable. In this case, if it will pass an identifier of the string x, we can return the x local variable. Okay, now let's compare our new extended syntax to the regular C++ syntax. Okay, so once again, we have two functions, one called f1 and f2. Each one uses the different syntax. Here on the left, you can see f1. And let me scroll down on the right so you can see f2. And they have the exact instructions. So once again, even with the extended syntax, this is zero overhead abstraction. All right. Also about the syntax, so our new costume syntax is linear, so it can be read from left to right. And we can also chain function calls with the pipe operator. So overall, we have created a more expressive syntax for this very specific kind of problems. Okay, now I have a question for you. Can anyone tell me if this code compiles? Well, the answer is no, but can anyone tell me why this code doesn't compile? What? Well, so this code doesn't compile because the int data member inside of C is private. So if you try to compile it, you will get an error. C is not a valid type for non-type template parameter because it is not structural. In C++20, the definition of structural type was modified to include context per variables of class type. But they must have these two following properties. All base class and non-static data members must be public and non-mutable. So all direct data member must be public. And also, all types of the base classes and non-static data members must be structural. So the entire composition tree must be public. So if you have even one nested non-public data member, you cannot use it as a non-type template parameter. Stud, tuple, and variant are not structural types because they have private data members. So I had to write my own basic version of them so that they can be used as a non-type template parameter. It took less effort and code than I expected, thanks to deducing this. Okay, so we saw how we can use compile-time parsers to create functions. Now let's use them to create types. We will create structs from this TypeScript-like syntax. So our parser will match an opening curly brackets followed by a list of data members where each data member is two identifiers separated by colon. And then closing curly brackets. Our output will be a list of data members where each data member is two identifier hashes for the name of the data member and the type of the data member. We can use this type wrapper class to pass around the type as a value. Then create a resolve identifier function that maps an identifier to a type wrapper. And that way we will be able to get a type by an identifier. We will use this struct member type to implement a single data member of our final struct. It takes an identifier and type wrapper as template parameters. It defines a getter function to get the data member by the identifier, and it also holds the data members that we want. Then we can combine multiple struct members into a single struct by inheriting from all of them. This is how the function that creates the structs look like. It takes the input string and the scope that will be used to map identifier. We first parse the input string to get the members, and then we create an index sequence for the members and expand it into parameter pack. We use a fold expression to create a struct member for each identifier pair. So the first one is the identifier of the data member, and we can pass it as is. The second one is the type of the data member, and we use the scope lambda to convert it from an identifier to a type wrapper. Finally, we can return the combined struct type as a type wrapper from our expand function. And this is an example of how our new syntax look like. Inside the struct macro, the text is converted into a string literal and passed to the create struct function. So far, the parsers and syntax have all been linear, but it is very common to parse trees. For our final example, we will see how we can use compile-time parsers to create tree data structures. And our target syntax will be JSON. First, we define aliases for array, object, and string. All of them will use a fixed capacity vector. We define a var as a variant of all the JSON data types. Notice that object, array, and string are all pointers inside the variant, so they are held as pointer and not the actual value. When we create tree data structures in runtime, we usually use pointers from a parent to a node, from a parent node to its children. Nodes are often dynamically allocated and should be preferably stored as smart pointers. Here we have an example of code that creates a JSON at runtime. If we try to make the JSON variable consexpr, we will get a compilation error because it refers to dynamically allocated value. You can use dynamic allocations in consexpr functions, but they must be deallocated and can't be stored inside the consexpr variable. We can solve this problem by using a compile-time allocator. Here we have a basic compile-time allocator that contains a tuple of fixed capacity vectors, one for each type. The add method stores a value in one of the fixed vecs and returns the reference that holds it. Now we can replace the calls to new with calls to allocate or add and store the JSON in a consexpr variable. We pass the allocator along with our input string to the JSON parser and store the result as the root of the JSON value. Below you can see an example of how to create. Here you can see that the allocator and the root are stored in the same struct because they must live together. And here you can see an example of how we can create a compile-time JSON from a string. The size of our JSON variable is very big because it contains the compile-time allocator. So how it will affect the binary size? So if it is only used at compile time, it will not be included in the binary output. If you do need to use it in runtime, then it must be included in the binary output. In this case, there are some ways to reduce its size. One way is to first run a lightweight parser to find what capacity is needed, and then just allocate based on the capacity that is necessary. Another way is to copy from the big capacity allocator into a smaller one based on the size that is actually used. When we use compile-time parser, the first thing to ask is, do you need a domain-specific language or a general-purpose language? Compile-time parsers are best suited for domain-specific languages. So if you need a general-purpose language, I recommend using regular C++. The second thing that you need to ask is, can your desired syntax be expressed with C++ operators? If so, then use operator overloading. The last thing to consider is how your domain-specific language needs to interact with C++. So the best examples and use cases for compile-time parsers are self-contained syntaxes, like regex or einsum. They don't refer to any outside variable, and so they are the easiest to use and implement. If you do need to access outside variables in C++, then you can either have explicit access by using an import table, like how Boost MetaParse interacts with the Haskell environment, or you can use, if you need a scope-based lookup, you can use a reflection with the resolve identifier mechanism that we have just seen. So which compile time library should you choose? If you are using C++ version before C++ 17, then your only option is to use Boost MetaParse. If you are using C++ 17 and above, then it depends how you prefer to write your parsers. If you prefer to create them by using parser combinators, use Lexi. If you prefer to generate them from an LR1 grammar, use CTPG. And if regular expressions suit your use case, then use CTRE. If you would like to try more experimental things with C++23, then you have the option of trying the macro rules library to see how Rust's macro rules can be implemented in C++, or use YACP to see like the complete implementation of the examples that we've seen here and how reflection can be used with compile time parsers. Okay, so about compile time error. How bad are they? So here we have two parsing errors. The first one is because I forgot to add a semicolon and in the end of main, and it is the kind of parsing error that I would like to get. This is from GCC. The second one is because I used the CTRE with a string literal and provided invalid regex syntax. From the error message, we can see that from the second error message, we can see that it failed in a static assert, which validates the regex syntax, and that there is a problem at position 4 of the string. While it provides enough information to understand what is the problem, ideally, we would like to get errors like the one above. And I'm not just picking on the CTRE library. From what I tested, this library consistently provided better compile time error messages compared to other libraries. So about compile time printing, there are ways to print arbitrary strings in C++20 to produce better error messages and warnings. Here you can see a link of how Vittorio Romeo used it to implement a compile time model, and I have a library that I used compile time printing to generate code at compile time. For more information, check the link over here. So how bad are the compile times? I'm guessing this is something you are all wondering. We will soon see some benchmark results, but keep in mind that they can drastically change depending on some things like the complexity of the syntax that you are trying to parse, the parsing algorithm used and how well it is optimized. It can change between compiler and compiler versions, and it will also depend on hardware and other things. So to get accurate results, you should run a benchmark for your own use case. But anyway, I still ran some benchmarks that can give you a rough estimate of what kind of numbers you should expect. So I used MSVC to compile in debug and release the examples we saw in the previous slide, which used my very unoptimized compile time parser combinator library. So the numbers that you see here are in seconds and are the average of 5 runs. I didn't include the variance because it was very small. At the top row of the table, you can see how long it takes to rebuild the entire project. And on the bottom row, you can see how long it takes to build the project without any of the compile time parsing code. So around 1.5 seconds difference. I generated another benchmark that compiles 1,000 structs by either using regular C++ syntax or by using the TypeScript-like syntax. I would like to clarify that you shouldn't use compile time parsers to implement structs, as they are better used for things that can't be easily expressed in regular C++ syntax. So parsing 1,000 regular structs and around 100 to 200 milliseconds over the baseline, and it's good to know that compilers are very well optimized for this task. With the costume syntax, the compile time parser adds another 14 seconds, which average to around 14 milliseconds per struct. One tip when writing compile time code is to try to make it similar to runtime code. It will be easier to understand, and they will use the same syntax, unlike with meta functions and template metaprogramming.
Debugging can be a lot easier because you can just remove the context per keyword, set breakpoints, and see what is going on in there. You can share the same code between compile time and runtime, so you don't have to write a different implementation for each. And it can lead to faster compile times and lower memory usage. For example, I wrote a different parser that parses a JSON into a template tree, and it took over 1 minute and 4 gigabytes of RAM instead of 1.5 seconds. And I have experienced the same behavior when creating large template trees with other compilers, so I recommend trying to avoid this when possible. Compile time parsers are not something new. They have been available in C++, in C++11, or arguably C++98. Their viability depends on the difficulty of writing and using compile time code and on compilation speed. Both have significantly improved over the years through language features, discovery of new techniques, compiler improvements, and faster hardware. And we can assume that they will continue to improve in the future. For example, in C++23, we get the if conteval keyword, which checks if a function is executed at runtime or compile time. And we can use it to have a different implementation for the environment it executes in. And as far as I know, in C++26, we should have support for user-generated error messages in static assert. So we can generate better error messages for compile time parsing errors. Eventually, we will reach the point where we will have a DSL for every domain, and they will all interact seamlessly through C++. Also, recently, there have been many talks about successor languages like Carbon and CPP2. Something that I thought of is that, in the future, when compile time parsing will be a lot better, maybe the next iteration will be just a compile time parser inside the C++ language. I have not tested anything about this approach, but I would like to get your feedback about it. Or we will all be replaced by AI. This is also a possibility, so I don't know. But my personal hope is that in a few years there will be another talk about compile time parsers, and it will show some of the code that you've seen here from C++ 17, 20, or 23, and it will say, look how difficult it was to do something that we can easily write in a few lines today. Anyway, thank you very much. Before we get into the question, I would like to say some words. I usually don't like talking about it, but I would like just to raise some awareness. So I'm from Israel. My country is currently at war. Many of my friends who are also software engineers are either mourning their loved ones who have been brutally murdered or left their family because they were called to serve in the army. So if you know someone in Israel, please support them, help them, say some kind words. I'm sure they will appreciate it. Anyway, if you have any question, you can ask them now or later.
So for the YACP library, I think there was, you used the greater and greater equals operators. So I've used megaparsec in Haskell. I don't know if you're familiar with parsec or megaparsec.
I'm not familiar with them.
They are monadic parsing parser combinator libraries. And so the greater and greater equals in Haskell, they are the monadic bind operators. So I was curious whether that played any role in, so if this is just a coincidence or
so it was the greater equal followed by lambda was inspired by the monadic bind operator of Haskell. The greater is used in many other libraries, and I think it is inspired by like cin, how you use cin to read the input. So I think, it is used like also in Lexi and Boost Spirit, and I assume also other libraries. So I'm not sure if, I think it is more inspired by the C++ streams than Haskell, but yeah, the greater equals is inspired by the Haskell bind. Nice for catching that.
Okay, thanks. Yeah, in Boost Spirit, there's also greater is used, but it's not really monadic, so it's like trying to be a little bit monadic, I think, from the syntax. But thanks for the.
Thank you. Okay, so
Just one thing, I think I like the talk very much, but for the measurements of compile time, there is like this tool, which is really nice to see. It's called F-time trace of a Clang, which gives you like breakdown, how much time it took, like let's say parsing source files, the optimization part. So it's really neat to, if you like profiling the performance of your compilation time, it's really neat tool to look into that, like to see where compiler took time in when generating things.
yeah, thanks for letting me know. I'll check it out. Okay, so thank you very much, everyone.